Vou. Tá bem?
Perfeito.
Legal.
So, well, it's a great pleasure to introduce Daniel.
Eu parei de te ouvir, Milton.
Também.
From time to time. Okay, so it's a great pleasure to introduce Daniel Valesin from Warwick University, who is going to talk about the scaling limit of an adaptive contact process.
Okay, thank you, Milton. Thank you for the invitation. Also, Claudio, he told me he wouldn't make it, but maybe he'll watch it later. It's a great pleasure to be back in IMPA, even in this strange way, but I'm visiting in October, so hopefully I'll pass by and see it in the real way. So this is this is ongoing work with Adrián, González, Casanova, and András, Tobias. We are finishing the paper in a few days, hopefully, and then it will be on the archive. And it's about a version of the contact process in which there are several types of individuals. And you can see it as a competition model, or you can see it as a contact process with adaptation. So I will start describing the model. And if this is the most, it's very important that everything be absolutely clear in this part. So if there are any questions, please feel absolutely free to interrupt me at any time. So we will take a model. Can you see the motion of my cursor? Is it visible, like the arrow? Yes, okay. So we will take the torus on ZD with size n, so z over nz to the power of d. This will be the environment for our process, and we'll define a continuous time Markov process. And here something is missing. So it's 0, infinity on to the power of the torus. So this is how we denote the process. So what it means is that every site of the torus can attain any value, any non-negative real value. So the state space is 0, infinity to the power of the torus. And the way we interpret this state space is that we say if you have x and t evaluated at v, so v here is a vertex of the torus. So if this value is 0, then we say that this vertex or this site v is empty at time t. Otherwise, if x and t of v is equal to some lambda larger than 0, then we say that v has an occupant. You can think of it as an animal living there, and the value lambda is also the type of the individual. So you can think that the space of types is the set of all positive real numbers, and individuals who are alive each has a type which is this positive real number. The dynamic, and so I will keep denoting the process. So there are these two indices. The first one is just going to indicate the size of the torus, because eventually we're going to take this to infinity, and t is going to indicate time. So how does this process evolve is as follows. There are essentially two mechanisms. Every individual independently die with rate 1. So this death rate is the same for everyone. So when an individual dies, the site becomes empty. And moreover, individuals, they try to give birth, and the rate at which they give birth is equal to their type. So if an individual has type lambda, it will give birth with rate lambda at each neighboring position. So if I have an individual at a certain site x, and I have a neighboring site here y, and here this has type lambda, it will give birth here at y with rate lambda, but it can only give birth at an empty location. So if the neighboring position is occupied, then the birth is forbidden. Then the child that is created when someone gives birth, the child will have the same type as the parent with a certain probability, but the child can also be a mutant. So the child will have the same type as the parent with this probability here. So first, it's maybe easier to see it as so let me delete this just to make it clear, easier to read, then I'll put it back later. So there is a certain probability that the child is the same type as the parent, and then there is a certain probability that the child is a mutant. So delta n b lambda. So okay, in this first case, okay, you just have a newborn individual of type lambda. But in case the child is a mutant, you choose the type of the mutant according to a kernel K. So here there are several things involved. There is this delta n, which is a positive real number. There is this b of lambda, so this is a function of lambda, and there is a probability kernel K, which makes you choose the type, which allows you to choose the type of the mutant when it's born. So the reason I had this minimum maximum before is just that I don't want these numbers to be well less than 1 or negative or more than 1 for probability. So that's why I have to put this. I guess here it's min. Now I will get it wrong. So it's delta n b of lambda here. Let me just go back to how it was before, so I don't make mistakes. Yes, no. Okay. Yeah, I guess this was min 1 delta n b of lambda. So the parameters that we have to define the model are essentially these. So we have these numbers delta n, which are we should think of them as very small. So they're going to 0 as n goes to infinity. We have this function b, which I call it the mutation rate function. And finally, I have this k, which I call the mutation kernel. Is the model clear? Are there any questions?
So, if I understand well, you could drop the b and have a kernel that. In that case, you could integrate B into the mutation kernel, but in that case,
I could, yeah. I want the mutation kernel to be a probability distribution, probability measure. So that's why I don't incorporate B inside it. Indeed. Yeah.
Okay, but okay.
Yeah, it will be kind of easier to read the formulas.
If you had a Dirac, okay, you could say your mutation kernel has a Dirac mass on lambda. And
okay, so I can also, I don't know if this addresses your question. So let me assume also that k lambda and then lambda is equal to 0. That you don't have jumps from, okay. That when you jump, you indeed.
Okay.
Yeah. So, but I really want it to be with this, to be a probability and without self-just.
So I have a question also, a very simple one, just to see if where I'm getting right the model. So, for example, if there is no mutation and well, maybe there is mutation, but
so if there is absolutely no mutation and you start with only type lambda, then you have a contact process. I will get to that in a bit. Indeed.
Okay. Yes.
And everybody gives birth with rate lambda and dies with rate 1.
Perfect.
So the way to think of it is that you have a contact process, especially when this delta is very small. You have a contact process, but every time you give birth, you have a tiny probability that that this child will now be a mutant, will have a different infection rate. And now in your torus, there are a few guys with rate lambda and a few guys with rate, say, lambda prime, and they are kind of competing. They cannot invade one another. They can only go to empty spaces.
Okay. And with no extra assumptions, do you still have this type of additivity properties of the contact process, or you need something else?
So additivity, well, you have to specify what you mean by that, right? So if you have a configuration and you add a new individual, say, you will get something that is above. So it's not going to be exactly additive in the sense of the contact process. There will be some, yeah. But I'll discuss this kind of thing in a bit.
Okay, thank you.
So let me say now what the assumptions are on these things, but I hope the model is clear at least. So there will be two assumptions. First of all, about these numbers delta n. As I said, these numbers delta n. So these are the numbers that get multiplied by the mutation rate function, and they are going to 0. So we're going to increase at the same time that we increase the torus. The torus is indexed by n. So when we take n to infinity, this delta is also going to 0. So it gets increasingly less likely that a mutation occurs each time there is a birth. But we assume that this delta n goes to 0 with a certain speed. So first, we assume that it doesn't go to 0 too fast. So we say that delta n is above 1 over n to the to some a0, some power here, and also that it goes to 0 faster than 1 over n to the d plus 1 plus some epsilon 0. So those are the conditions. And here I'm trying to explain why I want these two things. And I guess, yes. So the first condition that I'm taking here is that I would like, the first inequality, it's good. So if delta n goes to 0 too fast, then you could suppose that you start with a single type and you evolve the process. It could be that simply there is no mutation and the process just dies, meaning that at some point everybody is empty, so the whole torus is empty, and now mutation never happens. So that I don't want. I want some mutations to occur. So I insist that delta n doesn't go to 0 too fast. But also I ask for it to go to 0 at least fast enough that there is some that mutations are not too frequent. So, and this is kind of the main assumption. So this second inequality is sort of the main assumption. And what it's doing is guaranteeing that between one mutation occurrence, one mutation and the next, there is a time of order roughly n. So that, you know, when a mutant appears, there is some time. So a mutant appears, typically now there will be a competition between the host population, the population that was there before, and the mutant that appears. And the idea of this assumption here is that this conflict will be resolved before the next mutation occurs. So that these mutation events are well separated in space. So typically you will have one type living or two types living, but you will it's very unlikely that you ever have three types existing at once. It's not that it cannot happen, it's that it's becoming less and less likely that it happens. So here I'm kind of explaining why we, so just let's look at this. So when you let this dynamics evolve for a time of order 1, so for one second, let's say, the number of births that you observe is order of the volume of the torus. So it's order n to the d, because, you know, you have some guys who are occupied, some guys who are empty, and then the number of births that are occurring in one unit interval is the order of the volume of the torus. So if you take time not of order 1, but of this order here, delta n to the d minus 1, the number of births that you observe, well, you have to take this number, delta n to the d minus 1, and multiply it by n to the d. Because, well, in time 1, you get order n to the d. So in a time of this amount, you have to multiply by n to the d. So you get this number of births. So this is the time scaling that we will take. We'll take the time scaling delta n. And so this means that we accelerate time by multiplying time by this constant. So the idea of taking this time scaling is that in this time scaling, the time elapsed between two mutations is going to be of order 1 in this time scale. So we just and and this time scale is much larger than n by our assumptions. So this is how we will speed up time. So that is our first assumption for this. So it involves how fast, how this function delta, how the sequence delta n goes to 0. And the second assumption is a bit more technical, maybe slightly tricky to explain. So you can consider a Markov jump process on 0 infinity obtained from B and K. So let me explain what this means. So suppose that you have 0 infinity. And consider the Markov jump process on this interval that does the following. It stays still at a certain value lambda for a time that is exponential with rate b lambda, and then it jumps. And when it jumps, so it jumps to a position, let's say lambda prime, according to the kernel k. Then it stays at lambda prime with distribution for a time exponential b lambda prime, and then it jumps again choosing with. So this will give you a Markov jump process on the positive real line. And my assumption A2 is that I don't want this Markov jump process to be explosive. Explosive means that it does infinitely many jumps. It wants to do infinitely many jumps in a finite time. So this assumption will be important because later there will be a Markov jump process that will arise as a scaling limit. It's not exactly this one, but still this one will play a role in what will appear. Any questions so far? Is the model totally clear? Please feel free to ask if not. So there are several things. I hope there aren't too many things being defined. Once more, there is the delta n, which is a sequence going to 0. There's the b, which is a mutation rate function, and k, which is the mutation curve.
Just to make sure I understand, if b is bounded from above, then you're sure that your Markov process is not explosive.
Indeed. If b is bounded from above, but that's not necessary. But indeed, that's a sufficient condition. Yeah. So now let me say what we could prove about this model under these assumptions. So first of all, the assumption that we will make is that we always start with a homogeneous population. So at time 0, we have a population with a single, everybody's occupied by an individual of type lambda 0. And this number lambda 0 is larger than the critical value of the contact process on ZD. If you don't know what that is, I will explain it a bit later. But for now, let me just mention that there's a certain number that comes from the contact process, and this lambda 0 is larger than that. So we start at time 0 with a homogeneous population. So the first theorem says that the amount of time that the process spends in competition becomes negligible. So most of the time, there is no competition going on. There's only one type occurring. So what it says, if you define this y and t, which is just speeding up time in the way that I explained earlier. So this you do this time scaling that I mentioned, which makes it so that the mutation events are occurring in time of order 1 from each other. So you speed up time, and then you consider this thing here. It's the amount of time spent between 0 and t in which more than one type is present. So you just count or take the Lebesgue measure of the amount of time that is spent in competition, and the claim is that this converges to zero, to just a process that is identically zero. And this convergence is in distribution when n goes to infinity with respect to the square Hot topology.
So Daniel?
Yeah.
So in this theorem, when you say more than one type is present, just one particle of a different type means more than one type, or?
Indeed, yeah. So if you have everybody of type, let's say 15, and one guy of type, say 11, that's already counts as more than one type.
Okay, thanks.
You're saying that this thing converges as a process, but when you say that, does it contain more information that just?
No. It's the same thing as saying if you fix an amount, a fixed time t, it will converge to zero in probability. It's the same thing. Yeah. So that's the first theorem. It's not particularly deep. It just follows from the assumptions. But the second theorem is going to be more interesting. So we now define. So before I come with these formulas, let me more or less say what I want to do. So theorem 1 says that most of the time you don't have competition. You have a single type. Yeah. So now imagine that you take sort of a one-dimensional projection of our process, and this one-dimensional projection is just extracting the type that is there at that particular time. You know, so this will be like looking at the process and looking at who's winning at that particular time. Of course, if you happen to look at it at a moment when there is competition, then you have to come up with some cemetery state, or you delete those times, you do something, but those times are negligible anyway. So you just have to consider this process of who's winning. So this is what this process Z here that I'm about to define, what it does. It's a real valued process. You do this, you look at this Y and T, that is the after you speed up X and T, you get. So if Y and T has only one type, then you let Z and T be this type. Otherwise, you let Z and T be equal to the type that was most recently alone in the space, right? So if you happen to, if T is a time of competition, then you have to kind of look backwards in time and look at what was the type that most recently was winning. So this Z process is indeed showing you who's winning at a particular time, or at least most recently. Okay, so theorem 2 is that this Z and T, when you take n to infinity, is converges to a Markov jump process on the positive real line, and I will not tell you now what this process is, so I will leave some suspense here, these 3 dots, because before I tell you what the generator is, I have to introduce a few other things. But for the specialists in the audience, you can have fun trying to guess, see if you can guess what it is, if you're bored with the rest of the talk. Yeah, but let me say that it's not this one that I presented before, this one that I was drawing here. This is not the scaling limit, right? Because this one doesn't really, so it's not going to be this one. So these are 2 theorems, and if the statements of the theorems are clear, I will go on to some explanations of what is involved in the proof. And finally, the last thing I will say is what the generator is. So rounds of mutation and competition. Let's say, as I mentioned, we start from a single type, lambda 0 at time 0. And I want to define this stopping time here, capital Tn, which is the first time when a mutation occurs, the first time when a mutant appears. I'm going to split time into what I call rounds, and a round has 2 stages. Stage 1 is between time 0 and time Tn. So it's what happens until a mutant appears. And then there is stage 2, and stage 2 is what I call competition. And I take stage 2 to have a deterministic length of time. And that's just for convenience. You could also define another stopping time here and say, and define this stage 2 in terms of that. But yeah, there will be these 2 stages. The first one is until the mutant appears, and the second one is this moment when the 2 types are trying to compete to see who wins. And the idea of this number here, n to the power of g plus 1 plus epsilon 0 over 2, is that this will be more than enough for the competition to be resolved. So that's the choice, the reason for this. So it's more than enough for the competition to be resolved, but it's not enough for another mutant to appear. Because I don't want another mutant when the 2 types are fighting. I don't want a third type to appear. So this is the notion of a round. And then, you know, when the round is over, so there's a winning type again, then another round starts. So you have to wait until another mutant appears. You have to wait until the conflict resolves, and so on. So the process is split into these rounds. And the idea of what I'll explain now is that stage 1 of the round is going to look just like a regular contact process. And stage 2 of the round is going to look like what is called a multi-type or a 2-type contact process. Because, well, in stage 1, there's only 1 type, and in stage 2, there are only 2 types, typically, with high probability. So, so starting with stage 1, and here I have to very briefly explain what the contact process is. So the contact process, I'll denote it by zeta t in this talk. So zeta t with rate, infection rate or birth rate lambda on a graph. It's a process on the state space 0, 1 to the power of vertices of the graph. And the dynamics is given as follows. So here I wrote psi, but I should write zeta. So from a certain configuration zeta and at a certain site x, the 2 types of jumps that can occur is that you go from 1 to 0 with rate 1, and you go from 0 to 1 with rate lambda times the number of neighbors that are, again, this should be zeta, that are in state 1. So this is this model introduced by Ted Harris in 1974, and it's one of the most well-studied classes of interacting particle systems, and typically it's seen as a model for the spread of an infection. So 1 means infected and 0 means healthy. Contact process has, on ZD, has what is called an upper stationary distribution. So if you take the process on ZD and you start at time 0 with everybody in state 1, so everybody occupied or infected at time 0, and you run time to infinity, the process has a limiting distribution. So this limiting distribution is called, I'm going to denote it by mu lambda. So it's called the upper stationary distribution of the contact process. And then the contact process on ZD has a phase transition. So this is this lambda c, this number lambda c that I mentioned earlier, lambda c of ZD. So the phase transition can be expressed in the following terms. So if you take lambda less than or equal to lambda c, then this upper stationary distribution is just the trivial measure that gives probability 1 to the empty, to the all 0 configuration. Whereas if lambda is more than lambda c, then mu lambda is a non-trivial probability distribution, non-trivial and stationary distribution on the set of on 0, 1 to the ZD. So that's one way to express phase transition of the contact process on ZD. So I will mention some facts about mu lambda, the upper stationary distribution, and maybe you, so these are facts that are not so well known. So even if you know about the contact process, you might not have seen this before. So the first one is I'm going to define this number alpha of lambda. And I call this number alpha of lambda the effective birth rate. And it's defined as follows. It's lambda times a certain integral. So it's an integral with respect to the upper stationary distribution. So you sample a configuration from the upper stationary distribution. Then you ask if the origin is empty. So you want the origin to be empty. And then you multiply by the number of occupied neighbors of the origin. So this number, the reason I call this an effective birth rate is as follows. So lambda is what is called the birth rate, yes? So lambda is the rate at which one guy tries to give birth at a neighboring location. But sometimes the contact process has what is called a collision. A collision is when you try to give birth in a place that is already occupied. And when that happens, well, there's no effect. So you cannot, the birth is forbidden in that case. So what this alpha is doing is that you look at the contact process in equilibrium, so started from this measure mu lambda, and you look at, say, the origin or any site, and you look at the frequency at which indeed there is a real birth, so a switch from 0 to 1 at the origin. So this is not lambda, it's something else, yes? So it's some other number, and that's why I call it the effective birth rate. So here's the statement that for the process started from equilibrium, we have that if you take 1 over t times the number of births at 0 before t, this will converge almost surely as t goes to infinity to this number alpha of lambda. So that's the effective birth rate of the contact process on ZD. That's the first fact about mu lambda. The second fact is that I'm going to define sort of a biased version of or a weighted version of mu lambda, and I'll call it mu lambda hat. And mu lambda hat, here I'm giving the Radon-Nikodym derivative between mu lambda hat and mu lambda. So the Radon-Nikodym derivative is this thing here. It's at a configuration, it's the indicator that the origin is empty times the number of occupied neighbors of the origin. So that's exactly the same thing that appears inside this integral here. And the interpretation of this measure mu lambda hat is as follows. We see it as the distribution of the occupied landscape around a newborn particle in equilibrium. So again, suppose that you take the contact process in equilibrium on ZD, and suppose that you look at a moment when there's a birth at the origin. Yes, so you look at that moment, and you look in a box containing the origin. What you see there? What is the local configuration when there is a birth? So this has a probability distribution. Yes, and that probability distribution will indeed be this mu hat. So this mu hat, what it's doing is a sort of biasing of mu lambda, so that it looks like what you see around the newborn particle. So you will notice that here I'm insisting that I have 1 minus zeta of 0. So that means that the origin is empty. So when I say the landscape around newborn particle, I'm not including the particle itself. I'm excluding the particle. I'm looking at what it sees around it, but not counting itself. Yeah. So okay. So that's some facts about the stationary distribution of the contact process. And now I want to say a little bit about metastability of the contact process on the torus. And well, there are many references I could mention here, but I'm not citing anything. If you want references about the results I mentioned, I can. You can ask me and I can provide them later. But okay, so before, let me introduce some notation very quickly. So I introduce a bijection, I'll call it psi n, between a certain box of ZD and the torus. So so you just consider that you take a box, of side length n in ZD. So this n is the correct size, let's say, so that this is a bit annoying to define. So it's just the usual projection of ZD to the torus. So you could imagine that you take a box, and you project it to the torus in the natural way. So the origin mapped to the origin of the torus. So so we'll use this psi n quite often because we'll need to transport things from the torus to ZD. Okay, so now let's consider the contact process on the torus with rate lambda larger than, here it should be lambda c, larger than lambda c of ZD, and we start, so zeta n0 is identically 1. So at time 0, everybody is in state 1. And then there is this theorem that was proved by many people in several stages. I guess the first version of this result was in 1984 by Cassandro, Galvez, Olivieri, and Varis, only in dimension 1. Then there were other results in dimension. I think that the version that I'm stating here was proved by Mumford in the 90s. So what it says is just that the process will stay active for an amount of time that is exponential in the volume of the torus. So it will take very long for this absorbing state that is identically 0 to be reached. So there will be, although the absorbing state is reached with probability 1, it takes exponentially long for that to happen. By the way, a fun fact also for the specialists in the audience is that if I were stating this result for boxes of ZE, not the torus, but boxes of ZE, I could prove that actually the extinction time, so if you take the log of the extinction time and divide by the volume of the torus, then this would converge to a certain constant, to a certain positive constant. So that's a stronger result than what is here, because here it's just a lower bound. So that is known for boxes of ZD, but the proof doesn't really work for the torus, and I think it's not that easy to prove it. So I've been trying for a while, but it's not so clear. Okay, so now one observation is that if I take the contact process on the torus and then I take it at typical times of activity, what I mean by that is, suppose that I take a snapshot of the process at a certain time Tn, and this Tn is large, but it's small compared to the extinction time, the time when the process dies. So I want to take a snapshot of the process after mixing and before extinction, so to speak. So if I do that, if I take this sort of snapshot, and then I look, I claim that at that time I locally see mu lambda, this upper stationary distribution. So what that means is that, you know, you can take a local function and you take this sort of average here of, so you take the configuration, you shift it at this, so that this vertex V becomes the origin. I transport it to ZD, I evaluate the function F. So this is a kind of averaging procedure at time Tn. And then this will converge to, well, the test function integrated against the upper stationary. So this is mu lambda here. Upper stationary distribution. So the process is metastable, and locally the distribution that you see is the upper stationary distribution of the contact process when the process is active, which is kind of typical of metastability, right? There is this notion of well, fake equilibrium, this thing, this state of affairs that resembles but is not an equilibrium. I mean, in this case, that thing is well, looks like mu lambda locally. So, okay, I've been talking about the contact process and the contact process on the torus. Now I want to get back to my adaptive contact process. So this X and T, and here I'm just reminding you that I start at time 0 with everybody in a certain type lambda 0 that is above lambda C of ZD, and I take Tn as before, so time when first mutant appears. So that was Tn. And now I want to define this funny xn. This is going to be the position of this mutant. Position of the mutant born at time Tn. So what you observe at time Tn, so let's look at this equality together. So here I'm looking at the process at the time when the first mutant is born, but I'm shifting it so that the position of the mutant becomes the origin. Yes, so I'm centering the torus at the mutant, and then I claim that the process will look like this. It will be lambda 0, so there will be lambda zeros in a certain set A, and there will be one guy of the type lambda prime at the origin. Then I'm going to take this A here. So this A is the landscape that is faced, so the occupied landscape around the newborn mutant. Yeah, and I'm transporting it to ZD. So I get this LN here. So this LN is the occupied landscape around the newborn mutant. So what it sees when it's born, so to speak, but also transported to ZD. And then we prove this, this proposition here, that if you take this pair of random variables, so on the one hand, you take the time for the mutant to appear, but rescaled, as our choice of rescaling is this. So the rescaled time for the mutant to appear and the landscape around the mutant, this converges in distribution to a product measure. So they become, asymptotically, they become independent. And the time component becomes exponentially distributed with parameter b lambda alpha lambda. So b was our mutation rate function, and alpha was our effective birth rate of the contact process. And the landscape component becomes distributed as this mu hat, so this biased version of mu lambda. So yeah, so we prove that. I think here there's an idea of the proof for the first marginal, for the time marginal. Maybe it's best if I skip this explanation because I'm a bit afraid of running out of time. But it's nothing very deep. It's just saying, okay, let's look at a time t. What is the probability that a mutant has not appeared by then? So that's just 1 minus the probability that a mutant has appeared to the power of the number of births that occur until that time. The number of births is like volume times effective birth rate times time, and that's like an exponential to this part. So that's how it goes for stage 1. So to summarize what we learned for stage 1 is that, you know, you start with a homogeneous population. It will run exactly as a one-type contact process until a mutant appears, and the time it takes for that to happen looks like an exponential looks like it's exponentially distributed. And when the mutant appears, the landscape around it looks like this biased version of the upper stationary distribution of the contact process on ZD. Now we want to talk about stage 2. Stage 2 is this competition, the interval of time from the moment the mutant is born until some large time after that. And before I talk about stage 2 itself, I want to talk about the 2-type contact process, and I'll talk about it on ZD directly. So on ZD. 2-type contact process on ZD is an interacting particle system that was introduced by Claudia Neuhauser in '92 in her PhD thesis. And it goes as follows. So it's a process on the state space 0, 1, 2 to the ZD. And the interpretation is that 0 means the site is empty, 1 means there's a type 1 occupant, 2 means there's a type 2 occupant. And there are 2 infection rates, so birth rate of type 1, birth rate of type 2. And the dynamics is as follows. At each vertex, you go from any of the types, you die with rate 1, but also you switch from 0 to any of the types with rate lambda of that type times the number of neighbors. So in other words, you have these 2 types, 1 and 2, and they both die with rate 1, and they both give birth with rates lambda 1 and lambda 2, but the birth is only allowed at empty places, just like in the regular contact process. So it's impossible for a type 1 to give birth on top of an existing type 2 individual, and vice versa. So yeah, so this is the 2-type contact process on ZD. So I say birth with no invasion for the reason I just explained. So you have no births on occupied places. And now I will define this quantity here. So given lambda 1, lambda 2 larger than 0, and given a set A in ZD, not including the origin, I will define this function S. So S of lambda 1, lambda 2, and A. Definition is as follows. Imagine that at time 0, so I'm looking at this part of the formula now. At time 0, I put a type 2 guy at the origin. So I have a 2 here at the origin, and then I have type 1 individuals, so 1, 1, 1, and over the set A. So this is the set A here that I drew, and I put type 1's individuals there. and I put a type 1 individual at the origin, and then I look at the probability that type 2 survives, that it never vanishes from the population. So this is this function S of lambda 1, lambda 2, A. So it's the probability that type 2 survives when it's initially faced with a population of type 1 enemies occupying the set A, and type 2 only occupying the origin. We have studied this quantity in another paper, or I have studied it with Tom Mumford and Pedro Pantoja. In 2019, we proved this theorem that says that if lambda 2 is more than lambda c of ZD, and this is lambda c for the one type contact process, and also lambda 2 is more than lambda 1, so lambda 2 is the stronger type, then this chance of survival of type 2 is always positive, regardless of A. Of course, the most interesting situation is when you have a single 2 at the origin, and then everybody else is a 1. So what this theorem is saying is that even in that case, the type 2 has a positive probability of surviving, even though it's hard for type 2 to survive at first, at least, because it's trying to give birth, but it's only facing occupied sites. So we proved this result. There's also a sort of continuity statement, which maybe I will also skip. So what it says is just that, you know, if you have a set A and a set A prime, and they look similar inside, they look the same inside the big ball, then S is close. S with A here is close to S of A prime here. So that's also important. Okay, so again, I was talking about the two-type contact process. Now I will go back to my to the adaptive contact process, and I will take lambda 1, lambda 2, and suppose that lambda 2 is more than lambda 1, and lambda 2 is more than lambda c of ZD. And let's take a set A that is occupying the torus and doesn't contain the origin. Now, suppose that the process is, the adaptive contact process is started with a single mutant at the origin. So at time 0, now I take a type 2 individual at the origin of the torus and type 1 individual at type A. And I consider this, so I'm defining this quantity Sn of lambda 1, lambda 2A. So this will be a finite volume counterpart of this S. So this S was the probability that type 2 would survive forever on ZD in infinite volume. Now Sn is the probability that type 2 wins in the torus. Not that it survives forever, but that it wins the competition. And winning the competition means that by this time here, this time is the length of stage 2. By this time, you don't see any more mutation events. And by the end of this time, only type 2 is there in the population. In other words, type 2 won and no further mutation happened. That was, that's Sn. And the proposition that we prove is that this Sn is very close to S when you take n to infinity. And you can even take it, the statement is uniform over the choice of A. So the reason is there is a psi here is that, of course, A lives in the torus, so you have to transport it to ZD. So the Sn is close to S. It's getting closer and closer to S uniformly in A when n is going to infinity.
Can you hear me?
Mm-hmm.
Yeah. So when lambda 2 is smaller than lambda 1, then S lambda 1 lambda 2 is equal to 0, or? We don't know that. Okay. We don't know. Okay. We imagine that it's so it's a bit tricky because it could be that it could depend on the initial configuration. It's a bit tricky, but we haven't proved anything about that. We have only studied this quantity when lambda 2 is larger than lambda 1. And it's sufficient to describe the scaling limit. It's sufficient to describe the scaling limit. Indeed. Okay. Yeah. So speaking of describing the scaling limit, next section is description of the scaling limit, and then I'll be done. So so here's the generator of the limiting process. If you were trying to guess it, you can see now if you succeeded. So this is telling you with what rate. So I'm describing the, maybe I go back to the beginning. So I'm talking about the thing that appears here in this Theorem 2.
We're taking this process Z and T, which is after speeding up and after taking this one-dimensional projection of the process. So this is a one-dimensional process. It lives on, it lives on 0 infinity. And in order to define it, it's sufficient to present, the generator evaluated at a function f. So f here is a function, from 0 infinity to R with, let's say, a continuous, a smooth function bounded from 0 infinity to R. So, so here's the generator. It's given by alpha, which is the effective birth rate, times b, which is the mutation rate of the associated to lambda. So this is a parameter of the model. And then there is this integral. So I sample a configuration on 0, 1 to the ZD. So dA here is choosing a configuration on 0, 1 to the ZD. According to this measure mu hat is the equilibrium of the infinite of the contact process on ZD viewed from a newborn mutant. Then I integrate from lambda c to infinity, and I choose lambda prime according to this mutation kernel. And then I have this S function, S lambda lambda. So now I have chosen lambda prime in the second integral, and I have chosen A in the first integral. After I have chosen these two things, I take this function S, which I call the fixation probability, or the probability that the mutant wins the conflict. And that gives you the way that you choose lambda prime. So then you multiply by f lambda prime minus f of lambda. So in other words, this formula is talking about the two stages, right? So stage 1 is encompassed by this part here. So the mutant is, for the mutant to be born, you have to look at the effective birth rate of the contact process and multiply it by the mutation rate. And then here, this is how you end stage 1. So this is the landscape that is seen by the mutant once it's born. Then this integral here is deciding what is the type of the mutant. And then there is the fixation probability. And one observation that is the very last thing I'll say is that when we defined the process in the beginning, we didn't say that K was increasing, in the sense that in principle, it's possible from lambda to go to smaller values of lambda, right? So the kernel K is not necessarily supported on values that are above lambda. So in principle, it's of course possible for mutants to be born who are weaker than the host population. But what happens is that this possibility vanishes in the scaling limit, because when such a thing happens, when you have a weaker mutant born than the host population, this conflict will resolve itself very quickly. So the host population will manage to overtake these mutant guys very quickly, and in an amount of time that is not appearing in the scaling limit. So that's why the limiting process is increasing, even though the Z and T process is not necessarily increasing. Okay, so this is what we proved. As I said, this is very recent work. So if you have comments or suggestions, they're very welcome. Thank you very much.
So questions from the audience?
So, so you said that the process is increasing because of the weaker mutants cannot survive, but okay. So this means in your kernel that S lambda prime has to be 0 whenever lambda prime is smaller than lambda, right?
So at first we also thought that this would be the case, but in fact we didn't need to prove that in order to prove it. Because what you get is just that, you know, in the torus, if you have the mutant and you have a host population, you can say, so suppose that you have a small box inside the torus that is taken by the host. And the host is stronger than the mutant. Then you can say that after a while, this box that is taken by the host, it will pretty much grow. So now you have a box twice as big that is taken by the host. And then you can guarantee that the mutant is not there. It's maybe somewhere else, but it's not there. And then you repeat. So now you have sort of an increasing box inside the torus. and you can guarantee that the mutant is not there. So eventually this growing box will swallow the torus. So that tells you that the mutant is gone. But if you do that in ZD, it doesn't really work, because all you're doing is that you're guaranteeing that the stronger type is growing linearly in a way, but maybe the mutant is hiding in somewhere because you have infinite volume. So that's why we didn't need to prove it in infinite volume.
Okay, but I would say that as a corollary from your result, you would get that this thing has to be 0. Okay, maybe not for all A, but mu hat almost surely, right? Because if not, the process wouldn't be increasing.
So you're saying that you're making a statement about the two-type contact process on ZD. You're saying that as a corollary, we would get.
You would get this value has to be 0. Yeah, mu hat almost surely for A. No. Not
really. No. Because on ZD it can just go away. You know it in the torus eventually it will disappear just because the host is growing linearly and it will take the whole torus. But on ZD all you know is that
what I'm saying, I'm just taking your result as a given and saying, okay, if this is not true, then the process is not increasing.
No, it is true in our process. It is true. So you do put okay, I see the confusion. The point is that I put here on the integral. So the integral is support. I make it so I don't integrate below lambda. Yeah, I'm sorry, Uber. You're right. I should write lambda here. I should write lambda here.
Okay.
Yeah. I'm sorry. That was my fault. Indeed.
Okay, so you don't have a corollary.
Yeah, that was my confusion. Oh, I don't have a corollary. Indeed, yes.
Okay, thanks.
Yeah, thank you.
Other questions from here? Okay, let's see the chat if there is something there.
I have a question.
Yes, Augusto, please.
Yes.
Yes.
Have you thought about the similar problem on random irregular graphs? Is it similar, harder, easier?
So random irregular graphs, I think it's a good problem. I haven't thought about it. Of course, we would have to start by understanding the two-type contact process on the infinite tree, right? What it does. I'm not really sure if that has been done, but I think that could be a nice problem. Yeah, I think that's nice.
Nice.
Yeah. So if no more questions, I just a quick comment. I almost get your generator. No, I'm just kidding, but. Because it was much more complex than one could imagine at first sight, right?
Well, yes, I guess so. But maybe I've been looking at these formulas for too long, and it's kind of natural to me. But yeah, as I said, you can see it in terms of stage 1, choice of the mutant type, and then probability of fixation. So there are these 3 pieces, and they play a role. So that's kind of natural.
Okay, if no more questions, let's thank Daniel again.
Thank you. Thanks.
And well, thank you, Daniel. It was a really nice talk.
Thanks.
Thank you. Bye-bye.
Bye.